Alrighty, howdy folks. Chapter 5, Section 5. Inverse trigonometric functions and their graphs. I think the graphs of the inverse trigonometric functions, I'll talk about it in the end. But as such, inverse trigonometric functions. Let me first talk about that. And before I do inverse trigonometric, the special ones, let me just share with you some very interesting and important concepts of just regular inverse functions. If you understand the concept of regular inverse functions, understanding inverse trig functions becomes pretty simple. Cool? All right, let's get busy. What do I have here? This is what I want to ask you. Suppose I give you some generic graph of y equals f of x. It looks like that. Then I say, okay, can you find f of 2 for me? Based on this graph, you need to find what? F of 2. What would you do? Well, if you recall, all you need to do is go to an x value of 2, draw a vertical line there, see where it cuts the graph, and then notice that it cuts the graph, the vertical line cuts the graph here, and measure the corresponding y value. And that's going to be your f of 2. As simple as that. Cool? So how do you draw f of 2? Go to an x value of 2, draw a vertical line, see where it cuts the graph, draw a horizontal line there, and look at what the y value there is. Right? Okay. Now let me change the question a little. If I ask you now, hey, what is f inverse of 4? What is f inverse of 4? What would you do? Oh, for that, you go to a y value of 4, okay, and draw a horizontal line at that point and see where that horizontal line cuts the graph, and wherever it intersects, draw a vertical line and measure the x value, and that x value would be f inverse of 4. You cool about this one? This is all. If you understand this about inverse functions, boy, you have understood quite a bit. Everything else falls in place. Everything is actually hinging on this, and I'll try to demonstrate that to you. Cool. Now, just like Apollo 13, Houston, we have a problem with this concept. What's the problem? Earlier, I showed you a graph of y equals f of x that looked like that and talked about finding f of 2, finding f inverse of 4 and all that. But now, what happens if I wanted to find f inverse of 4 in a case like this, where y equals f of x looks like this? Oh, big deal, man. You do the same thing. You go to a y value of 4, draw a horizontal line, see where that horizontal line cuts the graph. Uh-oh. The horizontal line cuts the graph at 2 different points. So, is f inverse of 4 in this case the one on the left, or is it one on the right, or is it both? Right? Or you could say, oh, why not just make it both? Yeah, but the problem is f inverse is a function just as f is a function. Are you with me? F inverse is a function just as f is a function. But something we learned about functions long time back is, for one single input, you must get one single output only. Right? So for this f inverse function, If I give 4 as an input, apparently I get two different values. That's a no. That kind of a function, that cannot be a function when it does that. When it has a property of one input but two different outputs, cannot be a function. Right? That's a problem. Okay. Are there ways around it? Of course there are. Definition. Something called one-to-one function. What's a one-to-one function? A function f maps a into b. Oh, look at how I read that one. You read that f colon a arrow b as f maps a into b. Okay, a function f maps a into b is said to be one-to-one if x1 is not equal to x2, then f of x1 is not equal to f of x2. That's when we say the function is one-to-one. What? That means, let me explain. Graphically, what that means is, if I pick two different values for x, x1 and x2, x1 is not equal to x2, then their y values must be different. Is that condition satisfied by this graph? The answer is yeah. The moment I pick x1 to be one thing and x2 to be something else, then the y values are definitely different. I can do that to any 2 points. If I make this my x1, the y value is this. If I make x2 to be this, that's a different y value, right? But that condition is not true for this one. If I make x1 to be this x value and x2 to be this x value, they both have the same y value. F of x1 is in fact equal to f of x2, even though x1 is not equal to x2. That's the problem. Cool? All right. So clearly the function in the figure 1 is one-to-one, but figure 2 is not. Another one, definition, is horizontal line test. What in the world is horizontal line test? A function f maps a into b is said to pass the horizontal line test if no horizontal line intersects its graph more than once. For figure 1, no matter where I draw a horizontal line, that horizontal line cuts the graph at most 1 point, meaning maximum 1. It may not cut the graph at all, that's okay, but if it does cut, the horizontal line must cut the graph at only 1 point. Cool? Figure 1, the function in figure 1 satisfies that, whereas the function in figure 2 does not satisfy. I draw a horizontal line here, it's cutting the graph at this point and at that point. Right? Okay. Now, all of these, now let's actually get to the inverse functions definition. All that one-to-one function and horizontal line test, those concepts were actually needed for us to be able to define the inverse function. Let's get on with it. Let f be a one-to-one function with domain A and range B. You remember domain and range concepts for a function? Domain basically is what all values can you plug in and be able to evaluate the function. That's the domain. Range means as you plug in different values of x, all possible values, what are all the y values? What set of values will the y take? That's the range. Cool? Then its inverse function f inverse has domain B and range A. Right? If the function itself has domain A and range B, then the inverse function will have a domain of B, what was the range for f, and its range would be A, what was the domain for f, and is defined by f inverse of y is equal to x. Whoa, what's this funny looking thing? That's the symbol for what is called a biconditional, or if and only if. So when you see something like this, you should read that as if and only if. F inverse of y is equal to x if and only if f of x equals y for all y in B. I think I talked about this symbol meaning y is an element of set B, or you can simply read it as y in B, meaning y in the set B. Okay, let's try to understand this one. F inverse of y is equal to x if and only if f of x equals y for all y in B. Okay. The if and only if, what it actually represents is, we should be able to read this as, if f inverse of y equals x, then f of x equals y for all y in B. Okay. If the left-hand side is true, then the right-hand side of this biconditional is true. And at the same time, if the right-hand side condition is true, then the left-hand side condition must be true. That is, if f of x equals y for all y in B, then f inverse of y must be equal to x. That's the definition of an inverse function. I am almost certain that must have been clear as mud, right? But don't worry, I'll explain. In fact, intuitively, we should know that is in fact the case. What does it say? F inverse of y is equal to x if and only if f inverse of y is equal to x, then f of x must be equal to y, right? Okay. Would you agree? F inverse of 4, if I wanted to find that, I should go to y value of this and then draw a horizontal line. And so this is f inverse of 4, right? This x value is f inverse of 4. Now, when y is 4, the x is this particular one. Cool. Pay attention to this one. When y is 4, the corresponding x value is this one, f inverse 4. Okay. If that is the case, should it be the case that f of this particular x must be equal to 4? Yeah. I come over here and say, okay, find the f of whatever this f inverse of 4 is. Let's say some 3. Hey, what is f of 3? So you come to x equals 3, which also happens to be f inverse of 4, and you say, okay, f of 3 is 4. In other words, f inverse of 4 is 3 if and only if f of 3 is 4. Right? That is the idea. And implicit in the above statement is the fact that the inverse of a function f exists only if f is 1 to 1, right? That must happen. Otherwise, you end up with two different values. And so for a certain y, there must be only one x. And so the function must be a 1-to-1 function for an inverse function to exist. And properties of inverse function. Let f be a 1-to-1 function with domain in range B. Then its inverse function f inverse satisfies the following properties. Yeah, this is the key. F inverse of f of x is equal to x for all x in A in the domain. F inverse of f of x is equal to x for all x in A. Similarly, f of f inverse of x must be equal to x for all x in B. Now, let's see what the first one is. It's actually what I already explained. How do we evaluate these composite functions f inverse of f of x? we first evaluate the inside one and then evaluate the outside one, right? So when I look at f inverse of f of x, that means I will be given an input of x. I will give an input of x and then figure out f of x first. And based on the output f of x, I will then figure out f inverse. Okay, so let's do that. Let me pick x to be 2 and go to this graph to illustrate the purpose. X equals 2. I need to find f inverse of f of 2. Okay, f of 2. So let me go to x equals 2 in order to find f of 2. Like I said, draw a vertical line at x equals 2, find f of 2. Now, find f inverse of this y value. What do? You go to the y value, draw a horizontal line, see where it cuts the graph, and come down and measure the x value. Hey, guess what? We are back at 2. I have demonstrated this for a specific value of x equals 2, but that concept applies to every point in this one. Right? For every x value I can talk about that. Say x is equal to 1. This y value is f of 1. And f inverse of f of 1 would be, I draw a horizontal line, come back here. No wonder I would be back at 1. Cool. And likewise, if I wanted to find f of f inverse of x, that means we need to pick some value for, y, and find f inverse of that particular value. So let's make this x to be 4, and we need to find f inverse of 4 and then f of f inverse of 4. We do this. Go to a y value of 4, because we are wanting to find f inverse of 4. Draw a horizontal line, see where it cuts, and measure the x value. That is f inverse of 4. Okay, now f of f inverse of 4, go to f inverse of 4, which is this x value, draw a vertical line, see where it cuts, and you are getting back to 4. So f of f inverse of x is in fact equal to x as well. The question then remains, what's up with x in A for this case, but x in B for this case? Yeah, that is because, notice, in the first one, we evaluate f of x first, and then f inverse of that value. However, here, we evaluate f inverse of something first, and then the f of that output. Because first we find f of x, that means that x must be in the domain of f. Let me repeat that. Because we want to find f of x first, we can do so only if x happens to be in the domain of that function, and A is the domain. That's why we say for all x in A. And similarly, in order to find f inverse of x, we need to have x in the domain of f inverse. But earlier we said domain of f inverse is actually the range B, range of f, which is B. So that's why x must be in B. That's all there is to it. Cool. So once we understand about generic inverse functions, we can then go to inverse trig functions. So suppose I want to find inverse sine function. I didn't draw inverse. I notice how I didn't draw an inverse sine function directly. In this, just as when I talked about inverse function of f, did I draw the graph of y equals f inverse of x? I never did that. All I did is talked about that concept based on the graph of y equals f of x. That is precisely what I'm going to do here as well. In order to find the inverse of a sine function, I will first draw a sine function and glean some useful data from it, and then I will talk about its inverse. Cool. If the graph of sine function looks like this, can I actually find its inverse? Right? The answer is no. What? Yeah, I cannot find inverse function if the graph of sine, inverse of sine function, when the graph of sine looks like this. What's the problem? The problem is sine function is not one-to-one. In other words, sine function fails the horizontal line test. In other words, if I draw a horizontal line, that horizontal line cuts the graph at more than one point. So we have a problem. And this is where mathematicians decided, we recognize the problem, but we cannot just simply say, okay, let's dust our hands and get out of here and say, nope, there is no inverse sine function. Let's do something, they said. And they said, let's, no, since it's not one-to-one. And then they said, let's do one thing. When it comes to evaluating the inverse of a sine function, let's restrict the domain. Ooh, big word. Let's restrict the domain. What do they mean by that? That means let's not take the entire negative infinity to infinity domain of sine, but instead let's just take a piece of it. That means from negative pi half, x equals negative pi half, to x equals pi half, only this blue part of the curve. Is that one-to-one? Yeah, that just the blue part alone is certainly one-to-one because it does pass the horizontal line test. So by restricting the domain, we are in business. We can actually find the inverse of a sine function. Cool? A certain intelligent question should pop up in your head. Couple of them, in fact. The first one is, why negative pi half to pi half, man? Why can't it be, I don't know, 0 to pi? Oh no, 0 to pi? No, because 0 to pi means it still fails the horizontal line test. So that's a no. Okay, how about pi half to 3 pi half? Yep, that would work. That would actually work. Pi half to 3 pi half is still a one-to-one function, passes the horizontal line test. So why not that? Well, the answer is convention. Mathematicians sat down and said, yeah, let's pick this as the domain for sine. Okay, dudes? And everybody said, okay, that sounds good. Right? It's just mere convention. Okay. A second question that should pop up in your head is, as we are in the process of restricting the domain, why not just pick only the piece from 0 to pi half? Only that part. Why negative pi half to pi half? Can you answer that? Why not just the graph from 0 to pi half? The answer is, if we were to pick this and then I say, okay, find sine inverse of 0.5, would you be able to find sine inverse of 0.5? Yeah, you would. What do you need to do? Go to a y value of 0.5, which is somewhere here, draw a horizontal line, see where it cuts the graph here, and come down and measure the x value. And we know that would be pi over 6, right? Oh, okay, great. So for 0.5, we could find it. Now what if I said find sine inverse of negative 0.5? All right, I'll go to negative 0.5 and draw a horizontal line, see where it cuts. But we didn't include this one, right? If we were to erroneously limit our domain from 0 to pi half, restricted domain from 0 to pi half, that means this piece of curve doesn't even exist. We cannot let that happen. That means we cannot find sine inverse of any negative values. How could we do that? We would be shooting ourselves in the foot. We would be restricting ourselves unnecessarily. That's why the purpose, when we restrict, we make sure that we cover the entire range of the original function. And sure enough, by restricting from negative pi half to pi half, we are still including the entire range of the sine function, which is negative 1 to 1. That's another important point to know. Okay, the function is 1 to 1 and thus has an inverse function. Okay, what's the definition of a inverse sine function? The inverse sine function is the function sine inverse. You read this as sine to the negative 1 as sine inverse, with domain negative 1 to 1 and range negative pi half to pi half. Right? Sine inverse has a domain of negative 1 to 1. That means your inputs must come from this set negative 1 to 1. And your outputs must be between negative pi half and pi half. Pay attention to that part because we are going to need that. That's a very important point. Defined by, what is it defined by? Sine inverse of x is equal to y if and only if sine of y is equal to x. Okay. The inverse sine function is also called arcsine, denoted by ARCSIN, arcsine, right? So I might use them interchangeably, sine inverse of x or arcsine of x. Either one means the same. Sine inverse of x is equal to y if and only if sine of y is equal to x, provided these conditions are satisfied. Cool? All right, let's solve some problems and make sense of all of this. Recall the properties, yeah. So f inverse of f of x is equal to x for all x, and f of f inverse of x is equal to x. So that must be true even for sine and sine inverse. So sine inverse of sine of x is equal to x for what? Only if this x comes from that restricted domain of negative pi half to pi half. This statement is true. Otherwise, all bets are off. Cool? Sine of sine inverse of x is equal to x for all x in this negative 1 to 1, which is the range of the original sine function. Cool? All right, let me show you some problems. Sine inverse of 1/2. Somebody says, hey, what's sine inverse of 1/2? Excuse me. What you can do at that time is solution. To answer this, we ask ourselves two questions. You want sine inverse of 1/2? Well, is 1/2 in the domain of the inverse sine function? Okay. What is the domain of sine inverse? The domain of sine inverse is negative 1 to 1. In order to find sine inverse of x, x better come from negative 1 to 1. Is 1/2 in negative 1 to 1? Yeah. So we are in business. Yes, 1/2 is in negative 1 to 1. So sine of, then we ask the second question. Sine of what angle equals 1/2? But something else. Maybe let me explain it this way. So the second question, I will ignore this parenthetical expression for a second. Sine of what angle equals 1/2? Can you tell me sine of what angle equals 1/2? Sine of 30 degrees, or in terms of radian, pi sixths, right? But wait, sine of 150 degrees, right? That is sine of 5 pi sixths is also 1/2. So, should we say 5 pi 6 or only pi sixths? And that's why, in order to avoid that ambiguity, we say that angle must come from negative pi half to pi half. Pi sixths is certainly in this range, in this interval, but not 5 pi sixths. So that's why only pi sixth is the valid answer. Right? Sine of what angle? Pi sixths. So therefore sine inverse of 1/2 is pi sixth. As simple as that. In other words, typically what happens in my case, if somebody says, what's sine inverse of 1/2? I'll go, okay, 1/2, is that between -1 to 1? Yep, it is. Okay, sine of what angle is equal to 1/2? Pi 6. Is pi 6 in the domain of the inverse function, negative pi half, in the range of the inverse function? Yes, it is. So I'm done. Cool. Let's see. What is sine inverse? Negative square root of 2 over 2. What are the two questions you ask? Is negative square root of 2 over 2 in the domain of the inverse sine function? The answer is, yeah, domain mean inverse sine, -1 to 1. Yes, it is in -1 to 1. How do I know that? Square root of 2 is 1.414. Divided by 2 is 0.707, something like that. Negative 0.707. 0.707. Yeah, that is inside this. So what angle, sine of what angle in negative pi half to pi half equals negative square root of 2 over 2? Sine of 45 degrees or sine of pi fourths is square root of 2 over 2. So sine of negative pi fourths is negative square root of 2 over 2. As simple as that. So sine inverse of negative square root of 2 over 2 is negative pi over 4. What is sine inverse of 3/2? Should we ask the same thing? Two questions. Is 3/2 in the domain -1 to 1? Oh, it's not. Right? So, no, 3/2 is not in -1 to 1. Thus, sine inverse of 3/2 does not exist. Simple, straightforward. Sine inverse of 3/2 does not exist. Okay. What is sine of sine inverse of square root of 3 over 2? Didn't we say that f of f inverse of x is equal to x? So based on that, shouldn't this be simply square root of 3 over 2? Yes, but we got to be careful. Is square root of 3 over 2 in the domain of inverse sine? That's -1 to 1. Yes, square root of 3 over 2 is -1 to 1. So, because of that, we can say sine of sine inverse of square root of 3 over 2 is square root of 3 over 2. Now, what is sine inverse of sine of pi eighths? Same first question. Is pi over 8 in the restricted domain for the inverse sine, that is negative pi half to pi half? The answer is yes, it is. Therefore, sine inverse of sine of pi eighths is actually equal to pi eighths. Simple. What about sine inverse of sine of 2 pi thirds? Is 2 pi thirds in the restricted domain of inverse, which is negative pi half to pi half? No, it's not. Right? So what do we say? We say, do we say it does not exist? Nope. Check this out. Even though 2 pi thirds is not in negative pi half to pi half, because of that, we can certainly say this, sine inverse of sine of 2 pi thirds is not equal to 2 pi thirds. That we can confidently say, because it doesn't satisfy that condition. 2 pi thirds, the argument needs to be within the domain thing. However, this does not mean we cannot find the answer, because recall that sine of 2 pi thirds is sine of 120 degrees, and if we write in reference angle terms, sine of 180 minus 60, and 120 is in the second quadrant, so must be positive sine 60. Sine 60 is square root of 3 over 2. So we could potentially replace the sine of 2 pi thirds by a square root of 3 over 2 and ask our question again. Okay, sine inverse of sine of 2 pi thirds, but sine of 2 pi thirds is square root of 3 over 2. What is that equal to? Oh, that's sine inverse of square root of 3 over 2 is pi thirds, because sine of pi thirds, sine 60, is square root of 3 over 2, and this pi thirds is in the domain negative pi half to pi half. Right? Pay attention to all of that. All we did is, for 2 pi thirds, we can evaluate sine. And that's what we did. And then, sine inverse of this value, we picked the answer from the restricted domain of negative pi half to pi half. Even though 2 pi thirds itself was outside of the domain, and therefore we couldn't say sine inverse of sine of 2 pi thirds is 2 pi thirds, we could certainly do this because we have picked pi thirds from the restricted domain negative pi half to pi half. All right? So this is what we need to do. What else? Inverse cosine function. So in order to understand inverse cosine function, let's look at the graph of a cosine function. Can we directly find the inverse of a cosine function? The answer is no, because it faces the same problem of not being one-to-one, or that it fails the horizontal line test. So whenever something fails the horizontal line test, what is it that we do? We restrict the domain. So what did they restrict the domain of cosine here to be? They chose 0 to pi, this piece of the curve. Cool. So once you understand what the restricted domain is, everything else falls in place. What's the inverse cosine function is the function cosine inverse x with domain negative 1 to 1 and range is 0 to pi, defined by cosine inverse of x is equal to y if and only if cosine y is equal to x. The inverse cosine function is also called arc cosine, denoted by arc cosine, arc cos. Okay. I'm thinking I don't need to spend a whole lot of time because the concepts are exactly the same as what we did for sine inverse. Okay, or very similar to the sine inverse. How about inverse tangent function? Inverse tangent faces the same problem of not being one-to-one. However, the restricted domain in this case is negative pi half to pi half. Hey, that's the same thing for sine, man. Yeah, the only difference is negative pi half and pi half are not included, because at those values, tangent is undefined. At specifically negative pi half and positive pi half, tangent is undefined. Whereas sine did not have that problem. Sine of negative pi half is negative 1, sine of positive pi half is positive 1, so that was okay. So restricted domain is from negative pi half to pi half, and that's why you see this parenthesis and not square brackets like you did for sine. Cool. All right, where do we go? Same thing. Inverse cotangent, secant, and cosecant. Typically, people don't worry about cotangent and cosecant and secant for those functions. Okay, all right. Graphs of trig functions and their inverses. So can we actually draw the graph of an inverse trig function? How should I put it? I typically don't rely on the inverse graph functions. I just look at the original graph and based on it, try to figure out the inverse values. I don't necessarily draw the inverse graphs themselves, but for the sake of completeness, I'm doing it over here. Recall that the graph and inverse function of f is a reflection of the graph of f about the line y equals x. So this is a concept that you learned in pre-calculus and probably some other class, pre-calculus algebra. So if, let us say, I draw the graph of sine, the blue is the original sine x graph on the restricted domain negative pi half to pi half. So how do I come up with the graph of sine inverse of x, the orange one? Well, first draw the line y equals x, which is that 45-degree line, and then reflect this blue one about that y equals x. That's how I got this. Would you agree that this orange is a mirror image or reflection of the blue one? I'm sure you do, but you know what? Yeah, let me tell you how I actually figure these reflections about a line and all that. Suppose, without loss of generality, let's say I pick this endpoint here. Now my objective is to find what its reflection is about the y equals x line, right? I take a point. I want to know what its reflection is about the y equals x line. This is what I do. From this point, I drop a perpendicular line onto that y equals x line, a perpendicular line, and extend it. And the reflected point is definitely going to be on that perpendicular line, on the line perpendicular to the y equals x, passing through the blue point. What else happens? Because we are talking about reflection, distances must be the same. So the distance from this point to the y equals x line must be the same as the distance from this point to the orange endpoint. So that's how I find the reflected point. Cool? If I can do that to every single point, that is precisely what I do. Hey, what's the reflection of this point? Okay, drop a perpendicular onto y equals x and extend it. And look at how far you had to go from the blue point to the line. Go by the same distance, and that's how you get the corresponding orange point. That's the concept of reflecting a point about a line. And if you want to reflect the whole curve, pick every point on the curve and do the same thing. Cool. So y equals cosine x on the domain x equals 0 to x equals pi looks like this, and its reflection about the y equals x line looks like this. So the orange one is the cosine inverse x, the graph of cosine inverse x, and finally I got the graph of y equals tan inverse of x based on the restricted domain graph of y equals tangent x from negative pi half to pi half. Concept is similar. Reflect about the y equals x. Amigos y amigas, Adios.